Welcome everyone, and the topic of the today's discussion is the spectroscopy. What is spectroscopy? Spectroscopy is basically the study of the interaction between spectroscopy is the study of interaction between matter and radiations. when we say when we say that it is the study of interaction between the radiations and matter, now you must keep in mind that radiations are of two types. One are the corpuscular radiations and other are the electromagnetic radiations. What is meant by the corpuscular radiations? Corpuscular radiations are those that consist on particles and their speed is much less as compared to the speed of light. For example, beta rays that consist on electrons, alpha rays that consist on the helium nuclei, fast moving neutrons, cosmic rays. Cosmic rays consist of protons and other charged particles, so they are also corpuscular radiations. And all these radiations, they require some carrier, they require some medium for their propagation. And the second type is electromagnetic radiations. These are those radiations that do not require any carrier or medium for their propagation. Rather, they are propagated by the oscillations of the electric and magnetic field. And these radiations travel with the speed of light. For example, sunlight. No, I think so. You do remember that when sunlight is passed through prism, this sunlight is broken into three parts, or this sunlight is splitted into the three main regions. One is the visible, second one is the low energy, and third one is the high energy. Now the visible region that has wavelength range of almost 400 to 800 nanometer, and it consists of further 7 regions which are violet, indigo, blue, green, yellow, orange and red. While the low energy region has 3 main radiations: infrared, microwaves and radio frequency waves. These are the 3 regions which are present in low energy. These have low energy as compared to the visible region. And on the other hand, in the high energy, there are UV region, ultraviolet, X-rays and gamma rays. So these 3 types of the radiations, they have more energy as compared to the visible region. All these radiations are examples of the electromagnetic radiations. Now when we say that in spectroscopy we discuss the interaction between radiations and matter, so what type of radiations are the subject matter of the spectroscopy. Do we study the interaction of corpuscular radiations with matter, or we study the interaction of electromagnetic radiation with matter? So the answer is that these radiations are not discussed in the spectroscopy. Spectroscopy is actually the study of interaction between electromagnetic radiations and matter. When we say interaction, what does it mean? Interaction simply means that when these radiations will fall on matter, the matter will absorb some portion of these radiation. This absorption is actually the interaction. And very rarely, sometimes the radiations are also emitted. We will discuss it in the analytical chemistry, but in here, right at the moment, you are required to keep this thing in your mind that interaction means absorption. Matter, it means in spectroscopy we can discuss any form of the matter. We can discuss the elements, we can discuss the interaction of radiations with compounds, with mixers. So any form of the matter can be discussed. Now, before starting any particular type of spectroscopy, I will like you to recall some important and very fundamental terms that you have already discussed or studied in some very basic classes like 9th or 10th class. There are three important properties of electromagnetic radiations. The first is wavelength, symbol is lambda. The second is frequency, nu, and the third is wave number, nu bar. What is wavelength? The distance between two consecutive crests, or you can take two consecutive trough, that is called as the wavelength. It is the length of a single wave basically. And the SI unit of the wavelength, that is meter. But most of the times when we are discussing the electromagnetic radiation, we take its unit as nanometer or angstrom. And 1 nanometer is equal to 10 raised to power minus 9 meter. And 1 angstrom is equal to 10 raised to power minus 10 meter. Now what is frequency or nu? Frequency is basically number of waves passing through a point in 1 second. And its units are hertz or cycle per second. The last one is the wave number. Now the wave number, what is wave number? Basically wave number is the number of waves in unit length. Suppose that this distance is 1 meter. Suppose it. This distance is 1 meter. Now in this unit length, how many waves are there? There is only one wave. So its wave number will be 1 per meter. That is shown with the nu bar, and nu bar is equal to 1 over lambda. This one is a very important point. I mean to say that the wave number is actually the reciprocal of the wavelength. So these are three terms that you must have an idea in order to study the spectroscopy. These are three properties of the electromagnetic radiations. Now according to the Planck's quantum theory, E is equal to h nu. This one is first formula. It shows that energy of the radiations is directly proportional to their frequency. But frequency is equal to c over lambda, you know. So E is equal to hc over lambda. Putting this value here, it will be hc over lambda. This relation shows that energy of the radiations is inversely proportional to the wavelength. Being shorter the wavelength, more energetic the radiations will be. Now, this equation can be rearranged as hc into 1 over lambda. Now, what is 1 over lambda? That is nu bar. So, E is equal to Hc into nu bar. This shows that energy of the radiation is directly proportional to the wave number. So energy is directly proportional to two parameters, frequency and wave number. It means frequency and wave number are almost same things in terms of the energy. But wavelength is inversely proportional to the energy. Mean the frequency and wave numbers can be discussed simultaneously when we relate them with the energy, but the concept of wavelength, that will be quite different from them. These are the Planck's relations. These are the relations according to the Planck's quantum theory. So after the discussion of these basics of the spectroscopy, now let us start a specific type of the spectroscopy, that is the IR spectroscopy. What is IR spectroscopy? It is the study of the interaction of infrared radiations with matter. What is the principle of this spectroscopy? Suppose that there is a polar covalent bond between hydrogen and chlorine. Whenever a bond has certain dipole moment, the bond vibrates with a particular frequency. We are considering only covalent bonds in the IR spectroscopy. So, suppose if I show this hydrogen atom with a ball and chlorine atom also with a ball, then the bond between them will be just like a spring. So these two balls are actually connected with the help of the spring. And the bond is vibrating. There is a particular vibrational frequency of this bond. Now, if the infrared light or infrared radiations are thrown on the HCl sample, the HCl bond is already vibrating with a particular frequency. When the infrared radiation will fall on it, the bond will absorb only those infrared radiations or those photons that have frequency exactly equal to the vibrational frequency of the bond. So this bond will absorb only those infrared radiation that have frequency exactly equal to the bond's vibrational frequency. Now every bond vibrates with a particular frequency. It means every bond will absorb infrared radiation of a particular frequency. And those absorbed infrared radiation, they will be its characteristic feature. And the frequency of the infrared radiation that one bond absorbs, no other bond absorbs that frequency. So by looking at the frequency of the infrared radiations which are absorbed, much information can be collected about the nature of the bond. This is the principle of the IR spectroscopy. Now how do we study any sample in IR spectroscopy? Basically there is a source of what? Obviously IR radiations. Here the sample is placed and here is the detector. These are three main parts of a IR spectrophotometer. Now the source, what will it do? It will release some infrared radiations. Those infrared radiations are directed on the sample. And just suppose that our sample is acetone or propanone. Acetone is the special name or common name, and propanone is the IUPAC name. What is its formula? That is basically acetone. I have written this molecule in this fashion due to some reason. I want to show how many types of bonds it has. It has 3 types of bonds. Carbon double bond oxygen, which is carbonyl, carbon hydrogen, and the third bond is present between 2 carbons. These are 3 types of the bonds which are present in the propanone, and it is our sample on which the infrared radiations are thrown. When the infrared radiation will fall on this sample, obviously these bonds will be vibrating with some particular frequency, and these bonds will absorb only those photons having frequency exactly equal to their own vibrational frequency. So some of the photons will be absorbed, and those which are not absorbed, they are transmitted. Now the absorbed photons, they cannot reach the detector. Only those photons which are transmitted through the sample, they reach the detector. And then what the detector will do? It will make a graph. And this graph is called as IR spectrum. Because our sample was acetone, so this IR spectrum specifically belongs to the acetone or propanone. Now, on x-axis we have taken wave number. Keep in mind one thing, that whenever we are dealing with the low energy radiation, we consider their wave number. And when we are dealing with the high energy radiations like ultraviolet, like X-rays, gamma rays, or even the visible are also taken in the high energy radiation. When we are discussing the spectroscopy, we will consider their frequency. So wave number is present on x-axis, transmittance percentage is present on y-axis. Why? Because the absorbed photons cannot reach the detector. Only those photons can reach the detector which are transmitted. So we will have to take the transmittance percentage. Now look at this graph. How simple it is. Basically, there are 2 bands that we are required to discuss. The one is exactly at this band is exactly at 3000 per centimeter. So you can see that the transmittance in this case, that is very low. It means that those IR photons having wave number 3000 per centimeter, they are transmitted to a very less extent to the detector, but most of their portion is absorbed. So that is the first absorption band, and this absorption band is at 3000 centimeter, and it confirms the presence of CH bond, because it is the characteristic feature of the CH bond to absorb the IR photons of the 3000 per centimeter, and no other bond will absorb photons of this wave number. There is another region here. Here the again transmittance percentage is very low. It means, and that is almost to 1720 per centimeter. Because the transmittance percentage is very low, it means these photons are also absorbed. So which bond has absorbed these photons? That is the carbonyl, C double bond O. These 2 points are important in this graph, and the absorption band at 3000 per centimeter is for CH bond, while the absorption band at 1720 per centimeter is for the C double bond O. These are 2 absorption bands. Do you think that which one is more important, this first one or the second one? What do you think? According to me, the first one is not as much important. Why? Because there are so many organic compounds that have CH bond. So the first one is less important, but the main importance is of this region, C double bond O. This carries more importance. Why this carries more importance? Because that is actually the characteristic feature of this acetone. Mean it is the functional group of this acetone. So one of the main purpose of the IR spectroscopy is to detect the functional groups. What's about the other parts? What's about this region of the spectrum? We haven't discussed this region. Basically, every IR spectrum has two regions. One is the functional group region, and other is the fingerprint region. So this region of this graph is actually the fingerprint region. Now when we say that fingerprint region and functional group region, the functional group ranges from almost 5000 to 1300 per centimeter. This range is of the functional group region. And what information the functional group region will provide us? I have already discussed this, that it provides information about the type of the functional group which is present in a molecule. Now the rest of the portion, this one, that is the fingerprint region. So the fingerprint region is from 1300 to 667 per centimeter. And this fingerprint region actually provides us information about the identity of the compound. How? We have an unknown sample and we have a suspected compound, because we have an idea in our mind that this compound is suspected to be this one. What will we do? We will compare the IR spectrum with the IR spectrum of the suspected. So this fingerprint region will be basically responsible for the detection, because the fingerprint region of the unknown sample and the fingerprint region of the suspected compound is compared and we get the exact identity of the molecule. So that's why this fingerprint region is very important. Now there is a question that must be in your mind, that we have discussed only two bonds, C double bond O and CH bond. Why haven't we discussed the carbon single bond carbon? Because this carbon single bond carbon is IR inactive. What does it mean that it is IR inactive? It means this bond will not absorb IR radiations. Or if it will absorb IR radiations, that will be out of our consideration. Why? Because this bond has no net dipole moment. Whenever a bond has no net dipole moment, it is IR inactive. And when it is IR inactive, it is not in our consideration. So that's why this carbon-carbon single bond, that is not discussed in the IR spectrum of the propanol. If a bond is present between two hydrogen atoms, it is non-polar, no dipole moment, IR inactive. Carbon dioxide, no net dipole moment, IR inactive. So all those compounds that have no net dipole moment, they are IR inactive and they are not the subject matter of the IR spectroscopy. There is another question that we must discuss here, that the propanol has only 3 types of the bond, and out of 3 types of the bond, even the one bond is not the under discussion of the IR spectroscopy. Then why this graph is so complex? Because there are different vibrational modes of a bond. a bond has different freedoms of vibration, different vibrational modes. And how these vibrational modes are calculated? There are two formulas, one for linear molecule that have linear structure and other for non-linear molecules that have non-linear structure. For the linear molecules, the formula is 3n minus 5, and for non-linear molecule the formula is 3n minus 6, where n is actually total number of atoms. So n is actually the total number of atoms. For example, if we have water, now in water only one type of bond is present, that is OH bond. OH bond are present. There are two OH bonds in water. But these two OH bonds can vibrate in different ways, in different modes. And how these modes are calculated? You know very well that water is a non-linear molecule because of presence of its lone pair. So its vibrational modes, how many vibrational modes it has? Number of atoms are 3. So 3 into 3, 9. 9 minus 6 is equal to 3. There are two bonds of a single type, OH bond, but these these two bonds are one bond that will vibrate in 3 different vibrational modes, and that will make this graph very complex. Again, if we talk about the molecular vibrations, how many types of molecular vibrations are there? Broadly speaking, there are 2 types. One is the stretching vibration, in which the bond length is disturbed, and other is the bending vibration, in which bond angles are disturbed. The stretching vibration require more energy as compared to the bending. Now the stretching is again of 2 types, symmetric and asymmetric, and bending is again of further types, scissoring, rocking, wagging, twisting. So total types of molecular vibrations are 6. Symmetric stretching, asymmetric stretching, and these are 4 vibrational, molecular vibrational, which are of bending type, in which the bond angle is disturbed. If a molecule has only 2 types of bonds or only 3 types of bonds, the main thing is that it is not the number of bonds that are making this graph very complex, but these are actually the different vibrational modes and different number of vibrational modes that are making this IR spectrum very complex. So you must keep in mind how many types of molecular vibration are there and how the vibrational modes of a molecule are calculated. In case of HCl, it is linear and it has 2 atoms. So 3 into 2, 6, 6 minus 5, 1. So HCl has only one vibrational mode, and its spectrum that will be quite simple as compared to the complex molecules like acetone and even more complex molecules. So these are the different types of the molecular vibrations. Now at the end, let us discuss some advantages and disadvantages of the IR spectroscopy. What are advantages and what are Disadvantages. Of IR spectroscopy. The main advantages are that solid, liquid, gas, semi-solid, polymer, any state can be analyzed by using the IR spectroscopy. There is no limitation of the state that only solids can be analyzed, or only liquids can be analyzed, or only gaseous substances can be analyzed. It is fast and easy technique to perform, relatively inexpensive. Otherwise, there are some spectrophotometers which are very expensive, and even nowadays some modern techniques are used. IR spectroscopy is also a modern technique, but even more modern techniques are used in which very expensive instrumentation is used. The last one is it is very sensitive. Very sensitive mean that even microgram, if the quantity of the sample is in microgram, that can be analyzed by using the IR spectroscopy. And even there is another advantage, which is that the height of the peaks, the width of the peaks, height of the peaks, width of the peaks, position of the peaks, these provide very valuable information about the IR, about the compound which is being analyzed by the IR spectroscopy. Now there are certain disadvantages. The first one is this technique is not for homonuclear diatomic molecules like H2, N2. These cannot be discussed by using the IR spectroscopy. Even monoatomic ions cannot be discussed by using the IR spectroscopy. Complex mixtures or aqueous solution, they can also not be discussed by IR spectroscopy, because the IR spectrum will become so complex that it will not be valuable for us then. It provides us information about the functional groups, but the position of functional groups, that is not shown by the IR spectroscopy. Then molecular weight. No information about molecular weight can be obtained by using the IR spectroscopy. IR spectroscopy provides you information that how many types of bond are there. Like in acetone, there are 3 types of bonds. Only 2 were discussed by using the IR spectrum. But if we talk about the carbon-hydrogen bonds, how many carbon-hydrogen bonds are present in acetone? There are 6. But IR spectroscopy will only tell us the type of bond. It will tell us that acetone has CH type. But how many CH type bonds are present in acetone? This information is not provided by the IR spectroscopy, which is another disadvantage of the IR spectroscopy. So IR spectroscopy is for the detection of the functional groups in case of functional group region, and for the identification of the compound by comparing the IR spectrum of the unknown compound with the suspected compound in case of the fingerprint region. And the main focus will be on absorption bands. So IR spectroscopy is about the detection of the functional groups. Keep in mind, it is very important, because whenever you discover a new compound, the first thing, organic compound especially, the first thing that you need to know is to which homologous series it belongs, and then the further studies they start. It was an overview of the IR spectroscopy. As far as I discussed few moments before, there are different types of the molecular vibrations. These molecular vibrations cannot be shown on the board, how the atoms vibrate. So you must discuss it from the internet by you looking at the animations, at how these bonds they are actually vibrated in the scissoring, wagging, or rocking. Wagging, I can give you an example of the wagging. That is the movement of the tail of the dog. It is wagging movement. Stretching vibration, that is very simple. You can easily understand it. Stretching vibration, like if it is a molecule, if the vibration takes place in such a way that this atom moves in this direction and this atom also moves in this direction, then the overall, basically I think so, overall the bond length will not be changed in both sides. So that will be the symmetric stretching. In case of asymmetric stretching, bond length is disturbed because the direction of the vibration that is changed. So you will discuss other molecular vibrations from the animations. This was an overview of the IR spectroscopy, and I tried my level best to convey the basic concept of the IR spectroscopy to you people. It's all about for today. Inshallah, next time we will discuss some other modern techniques of the spectroscopy. Till then, Allah Hafiz.